So let's introduce some more vocabulary that goes along with sequences, and that is partial sums. Now, example H looks like one of the numerators of example F. Let me write that out again. So we've got this sequence, 2, 5, 8, 11. Can anyone come up with the next two terms?
14 and 17.
Yeah, 14 and 17. Thank you. 17 and so on and so on and so on. Now, each of these, let's see, we'll call this one B just for variety. B3, B4, B5, B6 is a term in this sequence. What we're interested in is the sequence of partial sums. So how's that going to look? Well, the sum of the first one term is just 2. That's our S sub 1. The sum of the first two terms would be 2 plus 5. That's our S sub 2. That's the sum of just the first two terms, so I get 7. S sub 3. What am I going to add up to get S sub 3?
Would be 2 plus 5 plus 8.
Yep, 2 plus 5 plus 8 would be 15. Because you're asked to find what's called the sequence of partial sums. So that's this stuff right here. Bless you.
Thank you.
Gesundheit.
So you want to find the first 6 partial sums. So that's S sub 1 through S sub 6. And one at a time, you're going to be adding up the first one, and then the first 2, then the first 3, and so on in terms of this sequence. So that's what the problem is asking for, which is why we're doing it. So it's, again, this is a lot of vocabulary that we're trying to impart to you in this section. S sub 4.
So I guess it's no, it's just, for that one, it's just looking at the terminology. Because I was about to say how you get that order, but it don't matter. Because you just add them to.
So we're just adding up the first 4 terms to get this one, and that would give me 26. Now, I am going to get a little bit fancy here on the last two, because I've kind of grown weary of writing 2 plus 5 plus 8 plus, you know, that kind of stuff. So how about if I do this? How about if I take S sub 4 and then add on the 14? So basically it's these plus the next one, and that's going to give me 40. And to get S sub 6, what's the fast way to get S sub 6?
5 plus 17.
S sub 5 plus 17. So well done. And that's your sequence of partial sums. Now you can write it all out if you want to, that's fine. I'm not going to give you points for or against it if you do or don't. But that's your sequence of partial sums. We're going to do that again for the next one. And the next one actually works out kind of interesting. So we might be able to figure out a pattern with that one.
That's the word I was looking for.
So example I.
Would you mind going back a little bit?
Yes, what's up?
How did you get 17 and,
Well, S sub 5 would be this plus this plus this plus this plus this, right? It's all 5 of them. But S sub 4 is the sum of these. So the only difference between S sub 4 and S sub 5 is I got that extra term. So I said, all right, let's take these terms, S sub 4, and then just add on that next term.
oh,
So, you know, some people might call it laziness, I call it economy of movement. It's just a little bit time saving there for us.
harder, not harder.
Exactly.
Okay, I guess.
So let's look back at this next one. A sub n equals 2 over 3 to the n. Let's write out the first 4 terms. A sub 1, A sub 2, A sub 3, and A sub 4. Ace, help me out with some of these terms, please. 2 over, well, 3 to the first power would just be 3. And then 2 over,
3 to the second power.
so 2 over 9.
Yeah.
And then 2 over,
3 cubed. 2 over 3 to the fourth.
27, and then 2 over 81. So those are the first 4 terms of my sequence. But now I need to find the first 4 partial sums, and then the general term for the partial sum, which sounds really daunting. If you look back here, I mean, how are we supposed to find a general formula for that? But let's find these numbers first. So we're trying to find the first 4 partial sums and the nth partial sum of that sequence. So we'll figure out what that is in a minute. S sub 1 you should be able to do pretty easily, right? 2/3. Yes,
Do you think we could just like put in our calculator and just go to fraction?
yeah. Well, let's make sure we put in the right things into our calculator. S sub 2 is gonna be what? 2/3 plus 2/9. And when you put it into your calculator, that's gonna give you 8/9. Oh, okay.
Hang on.
Oz is not so sure she trusts me on that.
No, I believe you.
All right,
I've never doubted you, bro.
okay.
We know you lied.
Annie, what do I have to add up to get S sub 3?
It would be S of 2 plus 2.
Yeah. So it's gonna be 2/3 plus 2/9 plus 2/27. And that one, interestingly enough, is gonna give you 26 over 27. So, okay. And the last one, S sub 4. Now, Annie used kind of a shortcut from our last one, I'll use it here. S sub 4 is just gonna be S sub 3 plus that last term. So let's do that, S sub 3 plus 2 over 81. And that's gonna give me 80 over 81. All right, so let's look at all these terms. I've got 2 over 3, 8 over 9, 26 over 27, and 80 over 81. We want to find a pattern in all this somehow. So one thing that I can do for myself, because I recognize something here, is play around with the denominators. The denominator here is 3 squared. What's the denominator with the third term? 3 cubed.
That one.
And that one's 3 to the 4th. So the denominator seems to be 3 to the 4th power somehow. Okay, that much I can believe. This is my S sub 1, S sub 2, S sub 3, S sub 4. I want to find S sub n. What is that going to equal?
2 times plus 2.
So it's gonna be something over
Something over, that's a
3n.
3 to the n. Good, it's something over 3 to the n.
Probably
That
3
would
to the
that's
5 to the 5.
Well, let's take a look up here. It's a little easier to see here. Look at the relationship between the numerator and the denominator.
It's always one short.
Ah, say that again. It's always one short, right? So how would I write that if it's one short?
3n minus 1.
There you go. 3 to the n minus 1.
Would it be
I think you wanna be me so bad.
n times 3 plus 2?
No, it won't work. You can try it for a few terms, but it won't match in the long run. This is going up as 1 less than 3 to the n. So what you gave me was a linear term, and it's not going to match that. It might for one term or two, but here's your general term. So you're asked for the first 4 terms, which we have. There's your first 4 terms, and that's your general term.
How did you get 3 to the n minus 1 again?
By looking at the relationship between the numerator and denominator. So the numerator is always 1 less than the denominator, right?
Oh, I see it.
This is 8, oh, that's 9 minus 1. 27 minus 1, 81 minus 1, etc. So that's how we got that part. Hannah?
Oh, wait, what did you say was in orange? You said the yellow was the general term and then the,
This is, you know, S sub 1, S sub 2, S sub 3, S sub 4. That's your general term,
oh, the oranges? It's circled down.
the circled in yellow.
Oh, okay, but what's the orange then?
Oh, those are S1, S2, S3, S4. So those were the specific ones. It asked for the first 4 partial sums and then the general one. So that's it. Okay, let's keep going. Yes, question?
No,
Something for,
no, I was about to be stupid. You really just said it.
all right. So we're gonna learn some more notation because you haven't learned enough yet. So these are examples
Are we finally down to
J, K, and L.
That stressed me out.
So what's stressing out Oz there is this fancy symbol like this. Yeah, and that's a Greek letter sigma. I usually don't try and draw it quite so crisp, probably just like that. That's our sigma. This is a capital letter S in Greek. Here's the lowercase in case you're curious. You'll see this one if you take a statistics class, is where you'll see sigma. But for what we're doing here, this again kind of has some roots in programming or something you'll see in programming, kind of like a for loop or a while loop or a do loop, etc. The notation is k equals 2 to 4 of 1 over k. And it looks messy, but it's not. It's actually wonderfully compact notation. It's asking you one at a time to plug in the integer values between 2 and 4 into this expression here. So let me kind of highlight that in blue. We're going to substitute the values of k into that expression. So at k equal 2, I get 1 over 2 plus, and I'm going to keep going, k equals 3 gives me 1 over 3, and k equals 4 plus 1 over 4. And that's it. That's all they're asking you to do, is sum up these integers, or not these integers, these expressions. So if you turn these all into something over a denominator of 12, you'll get 6 plus 4 plus 3, you'll end up with 13 over 12. And that's it. That's what this is equal to, 13 over 12. There's a lot of convenience in this notation. Part of the battle in mathematics is not only coming up with a good notation, but understanding it and getting comfortable with it. You're catching up on thousands of years of human history of working with math. And believe me, if you ever read some old text with some of the old notation, I mean, just think about Roman numerals. Try and multiply in Roman numerals. Good luck. No thanks. All right, let's try another one like this. Again, we're going to expand a sum. So the next one here is the sum from k equals 1 to 5 of 2 to the k minus 1. So this is what you're going to plug into. That's your summons. It's not a term that you need to know. But one at a time, you're gonna plug in different values for k. Where do you start? What's the lower summation here?
1.
So k equals 1. That's gonna be 2 to the 1 minus 1. And then 2 to the 2 minus 1, and so on. K equal 3, 2 to the 3 minus 1, k equal 4, 2 to the 4 minus 1, and k equal 5, 2 to the 5 minus 1. Let's put in those numbers that you're missing there. Let's see, there we go. 1, 2, 3, 4, and 5. You're adding these up as you go. So that's 2 to the 0, plus 2 to the first, plus 2 to the second, plus 2 to the third, plus 2 to the fourth. And if you take out your calculator and grind these all out, 1 plus 2 plus 4 plus 8 plus 16 gives you 31. Now, my interest here is not necessarily to get the number 31. It's just to help you understand this kind of notation. You don't have to use the variable k. The variable you choose here can be anything. Typically speaking, we use I, j, and k as the indexes for these kinds of problems, but you can use literally any letter that you want.
I'm just kidding.
Okay, let's try one last one. Now this one last one's a little bit different. We got the sum from, what was it? I equals 3 to 15
And it's, yeah.
of 5. What's different about this one as opposed to, say, our previous two?
You start out at 3 instead of 1.
All right, we start out at 3 instead of 1. There's something else that's different too.
It doesn't have a variable.
Yeah, it doesn't have a variable. So
Is it 3
let's,
factorial?
nope.
Oh, damn.
So let's just watch here. When I equals 3, I get a 5. And then I equals 4, I add another 5. In other words, this expression isn't changing.
So when I equals 15, it's gonna be 5.
Yeah, when I equals 12, when I equals 11, when I equals 13, 15, it's always just gonna be 5. I equals 6, 5, I equals 7.
Just 15 times 5, man.
It's not 15 times 5. It's good you're thinking about multiplication. You don't want to do this by multiplication, or you don't want to do this by addition, although you could. Definitely want to take advantage of multiplication if you can. Plus 5, that's I equals 9. Plus 5, I equals 10. This is getting boring. I equals 11. I equals 12. I equals 13. I equals 14. And I gotta squeeze in the I. And I equals 15.
Oh, that makes sense. Yeah, you can't multiply because you skip one and two.
Oh,
So yeah, you gotta be a little bit careful. Now, my morning class said, 15 minus 3 is 12, 12 times 5 is 60, but that's not the answer here, is it? What is the answer?
65, is it not?
It's 65. Now,
So I was right.
how are you gonna find this in general? What's the trick? Now, I hope you didn't just sit there with your calculator and go 5 plus 5 plus 5 plus 5 plus 5 plus 5. I don't want that.
I didn't do that. I did it.
I don't know.
I
You got any
had already
witnesses?
figured it out.
Nick, was she wailing away on her calculator plus 5 plus 5 plus 5? He threw you under the bus. All right.
You lied to me.
Don't worry, Nick, we'll get you an escort to your car. All right. All right. But here's the trick. You have to count the number of terms in this summation, in this series is what it's called. And the quick way to figure that out is to take this index minus this one plus 1. And I want to write that down for you because you're going to need that. So
Look at me, I am on it, like right on right.
the number of terms in the summation, there should be an M here, summation, is the top minus the bottom plus 1. So in our case, it's going to be 15 minus 3 plus 1 equals 13 terms. And now that you know you have 13 terms, you can say, okay, well, it's going to be 13 times 5 gives me 65. That's the summation of this expression. Ah, okay, that's not so bad. That's a worthwhile result, and that's why I took the time to write it out.
So any equation that's similar to this, you could use that top minus bottom.
Absolutely. So for instance, if you had, say, another example, the sum from, let's go with j equals 63 to 2072 of, I don't know, 6. Then I hope you wouldn't be sitting there and typing out 6 plus 6 plus 6 plus 6. What you would do is realize that the 6 plus 6 plus 6 quite a few number of times. So let's figure out how many times. So it's going to be 2072 minus 63 plus 1 times. And so that's going to be 2010. No, come on, look. You add the 1 there, you get 2073, and then you subtract 63. It's pretty easy. That's not a human calculator.
But you see how you did that quick? I would've had to 2010, see that's
So this is really 2010 times 6, which is 12,060. So a lot better. I have literally seen students write a bunch of 6s on the back of their exam.
They're better than me.
I mean, completely covered it in 3-point font
Hey, don't y'all be
and
laughing,
tried to answer. And I was like, wow.
cause I would do that.
I give them a point for effort, but their answer was way wrong. And I don't want you doing it that way. I want you to do it this way, all right?
Can you
Yes.
remind me why you did that plus 1?
Yeah, because there's an extra term in here that you're kind of not seeing when you go, if you did 15 minus 13, or 15 minus 3, you'd say, oh, well, there's 12 terms. But when you count, and let's do it together, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. There's 13 terms here. Now that gets kind of hidden if your count starts at 1. 5 minus 1 is 4, plus 1 gives you 5. There's 5 terms here, so you don't have to think about it when there's 5. Or, pardon me, when it starts at 1. But if it starts at something other than 1, like 4 minus 2 is 2, plus 1 gives you 3 terms. So if you're starting at something other than 1, then you got to keep in mind this little idea. The number of terms is the top minus the bottom plus 1.
So it's just like not forgetting that original value you started with.
Exactly. Yeah.
Just a way to think about it.
All right.
Wanna bring it down a little quick?
Hold it down,
Bring it down, bring it down.
Can you go up just a little bit?
hold it down.
All right. Yalla, yalla.
Just take a picture.
Okay. Let's look at the next one. So the next one looks like this. K equal 4 to 7 of k times k plus 2. How many terms are there going to be in this summation?
3?
Wait, so you gotta add 1. So it'd be 4 minus 7 plus 1.
7 minus 4 is 3, plus 1 is 4. So there's going to be 4 terms here. n equals 4,
I said 4 first.
gives you 4 times 4 plus 2. Add n equal 5. I get 5 times 5 plus 2. Are you comfortable with this summation notation? Can you plug in these other ones? Get n equals 6 and n equals 7 to finish this off with. Six times 6 plus 2 plus 7 times 7 plus 2. So in other words, 4 times 6 plus 5 times 7 plus 6 times 8 plus 7 times 9 . So 170. And that's it. Ask you to write it without that summation notation. By the way, quick brief aside here. Not that many of you heard of this guy. Maybe you've heard of Newton. Maybe you've heard of Archimedes. But a lot of people probably haven't heard of a guy by the name of Carl Friedrich Gauss. And I'll talk about him later. And I'll show you how he was able to do what he did. But when he was in class in 19th century Germany, back when they had chalk slates instead of pen and paper, his math teacher got mad at them and asked them to do this summation. Can you tell me what that would mean if you were to write it all out? What is this? What is he being asked to do?
Maybe 1 is 100, 2 is 100, 3 is 100, right?
Nope.
Oh, damn. Is that not the same thing we just did?
Well, it's the same kind of thing, but it's going to be 1, and then you go to the next one, plus 2, plus 3.
So all the way to.
Wait, so why wouldn't it be all 100 like how we just did?
Because I don't have 100 here, it's J, and J is the index, so that keeps on changing. If I wanted all 100, I would wrote 100 there.
Like how 5 was over there. Oh, okay. My bad. You're right.
Now, he was 10 years old at the time his professor gave him this problem
They were doing that at 10 years
in a whole class, and the professor thought he'd keep him busy for a while. Little Gauss just kind of looked at it for a minute or two and then wrote down one number. Can anyone tell me the correct number that I would have to write down for the summation? Now keep in mind, a 10-year-old did this on the fly. And he put his number on a chalk slate, tossed it up on his teacher's desk really cheekily and said, there it is, and sat back down. And he was the only person in the classroom to get it right. And that answer was 5,050. Wow, that's pretty good. We'll see next time how he is able to do that. But even knowing how it's done,
Next time.
it's still impressive.
What do you mean? You gonna
I
put
mean,
the
next time.
cliffhanger?
There's, yeah. This is
Why
a
would
to be continued because we've only got a few minutes left
Okay,
and I
that's
need to,
more than enough time.
I need to finish off these 3 examples.
Oh.
We'll see. Remember, there was a little something extra I gave you an opportunity to do as well.
I just.
Let's try this one. This one, we're gonna kind of go backwards. We're gonna start out with the summation notation, or we'll start out with the sum here, but now I wanna write it with summation notation. So I wanna write it as the sum, and let's agree on a variable. Do you want to use N, K, J, I, whatever? What variable do you wanna use? I? So I equals, and then we gotta write something that would give us this sum when it's all expanded out. Now you should be able to see the general pattern of these terms. So you want to write I to that, pattern here,
I swear.
and then you want to start and end your summation at the right spots.
So would it be no, it would be 10 at the top, right?
10 at the top.
And then I don't know the
Well, where does it start?
1.
1 at the bottom. So from 1 to 10 of,
I square.
and I'm afraid that's it. What's that?
Is that for example O?
Yeah, that's for example O. I can make it harder?
Absolutely not.
No?
Nobody asked for
That
that.
was a.
No? All right.
Oh, we just skipped over example F.
Well, I wanted to do this one first because it's a little more concrete. Here, you know where you start and you know where you end. It's 1 to 10. Up here, it's similar, but instead of ending at 10, where are we going to end our summation at?
And
N. So that's the only difference. So I wanted to give you a chance to try something concrete before we did something a little more abstract. Why don't you try this one next? So sum from, and let's use J this time. J equals something, etc. See if you can't figure out how to write this one with your summation notation. I'll volunteer on this one. You got this one?
yeah.
All right, Sabira, go ahead.
Above it will be, J will be 1, and then above will be N,
Good, 1 to N.
and then fraction square root N,
We'll have to use a J here. Square root of J,
square root of J, okay, and then J to the 4th.
and that's it. You've got your general term right there. We just had to rewrite it with the variable that we have here, our index of summation. But that's it. That's all there is for that one. Nice. Our last example here is N. But before we go on to N, are we okay with that one? All right.
Which one was that?
N, Amber?
Okay.
Okay with that one? All right. All right, let's take a look at example N. It's asking you to calculate basically how much money you're gonna have in the bank at 2.4% interest compounded monthly as a function of time. So you don't need to be able to unravel this expression in terms of the story problem I just dictated, but let's put this expression into our calculators and get it to give us the first 6 terms of this sequence.
So do we put this in like the table again?
Yeah, we're gonna eventually do a table. So I'm gonna go up to my y equals term and clear this out. Let's put in the number 2,000, parenthesis, 1 plus 0.024 divided by 12 and raised to the n power. Now you don't have to worry about the first term in this. In fact, I'm gonna delete that just out of good measure. But there's our expression. And to get the first 6 terms of this sequence now, what I can do is just go to the table function and get those first 6 terms. Now, when you're all done with this problem, remind me we're gonna have to get out of this mode, but hit the second key, then the table key, and I've got a bunch of these numbers already. It does ask you to round to the nearest hundredth. Oops, 2 and 3. There we go. Now the first 4 of these are nice and even. Actually, they're not. No. So to see the complete decimals on this, what you need to do is you need to put the cursor on the y coordinate or the second column, and then scrolling up and down, you'll be able to see those values on the bottom of your calculator. And from there you can round. But I wouldn't necessarily put these in one at a time. I would definitely take advantage of the table value for your calculator to put those in. So, are you able to get those numbers on your calculator?
Yeah.
Annie? Are you able to get these numbers on your calculator?
Okay.
All right. Dalen?
Yes, ma'am.
No?
I don't know how to get there.
All right, so I put it in here first. put in that equation. And then, once I have that equation in, I hit the second key, then the table key
Put your calculator in
to get
there.
over.
You weren't here when he told us to put the calculator in there.
All right,
You gotta
yeah,
see
we'll have to do that one after class then. Any other questions on this last one? All right then, let's put this one in the books.